Okay, good morning, everybody. Thank you for joining this session. I'm really pleased to have Peter here, who had to wake up at 5 a.m. at least to do this presentation. So thank you so much, Peter, for agreeing to present at GEC, and the stage is all yours now.
Thank you, Anna. How is everybody this morning? So it's even morning for me, which is 5:30, but for you, I know in England it's 10:30. And I see we have some people on that are not just from England. So welcome, everybody. My name is Peter Enrico with Enterprise Performance Strategies. And I want to thank you and welcome you for joining my session today for GSE. And the title of the session is Evaluating Latent Demand in a Mainframe Environment. So hopefully you learned something today. I enjoyed putting together the presentation. And as Anna had mentioned, the chat is open. So if you have any questions, I'll be monitoring the chat. Feel free to ask along the way. I may not get to it all during the presentation, but I'll be certain to get to the Q&A or comments and questions certainly after the presentation as we have time. So let's just get going. So evaluating latent demand in mainframe environment, just a couple of, hold on, got to go to my advancement here. Here it is, I'm sorry. So, I'm sorry, I got my, there it goes. Abstract. Just for those of you who don't know, as a quick little commercial, one of the things we do, or three of the things we do for a living, is we do performance analysis reporting. So we have our Pivoter product, so hopefully you'll be interested in looking at that sometime. All the graphs in this presentation is from Pivoter. The other thing we do is performance and mainframe education. We teach 3 classes this year, and probably the beginning of next year, we're going to be teaching them over the web. We've been getting some really great feedback on them, especially since they're web-enabled now. And all of our classes, we have a basic tuning class, a workload manager class, a parallel assist class. But what's interesting about all the classes is before the class, you send us a set of data, and then in class, you will be analyzing your own environment, your own data. So think of it as a week of learning as well as a week of doing. We do some level of performance consulting, which is our war rooms, which have been highly successful, which are intense efforts to do, for performance analysis. But mostly what we also do is disseminate information, which again, thank you for allowing me to present here. One thing I do want to mention is that I did start a mainframe performance channel on YouTube where we've been regularly adding videos. We've only been up for a few weeks, so there's not many videos out there. There's maybe 15 or 20 videos out there. But hopefully you subscribe to the Mainframe Performance channel, where we will be providing regular videos on a regular basis. And they're going to be educational videos. So right now I just posted a video. I'm about to post a video on CP Enable, as well as other subjects. So if you have something you want me to present on the video channel, myself and Scott will be doing this. My colleague Scott Chapman, maybe we get Anna to do a video for us. Who knows? Any one of you can do a video as well. So take a look at the Mainframe Performance channel. I'd love to have you as a subscriber. And then finally, what we do is we also provide webinars on a regular basis. And this is our fall lineup for our webinars. You can see we have about 10 webinars lined up. I think we already gave one of the first ones. But these are pure educational webinars. They're only half an hour in length. Maybe they sometimes go to 35 minutes. But we really try hard to cover an assortment of subjects. So hopefully what you see is from the Performance channel on YouTube, between these webinars, we are everything about ZOS performance, so join us. But we want to talk about latent demand today. And latent demand is sort of an interesting subject because if you have any sort of weight enforcement, capping, machine capacity issues, chances are you also have latent demand. So what latent demand is, if you don't know already, is work that is waiting to get done but can't get done because of something in the configuration is preventing it from being dispatched. We have work that wants to use the CPU, for an example, but something is preventing it from using the CPU. And if you give the analogy of going to the bank, think of the line of people trying to get to the tellers is backing up. And that's kind of what latent demand is. We can easily tell it's latent demand, but I'm going to go through some exercises just to show periods of time that you typically do see latent demand. We don't usually know how much CPU the work wants to use when it gets the CPU, which is always a problem. It's not always a case where, oh, look, the queue of work waiting to use the CPUs is backing up. What we don't know is how much CPU they're going to use. I mean, we've seen cases, I'm sure you've seen cases where you have long queues of work backing up, and each one wants to use the CPU very quickly and very little. So the queue winds down very quickly. And there's other cases, of course, where the work that wants to run is very CPU intensive, very long running. And even as it gets dispatched, the queue doesn't build down very quickly. So it's really a guesstimate in terms of how much CPU you actually want to consume once the in looking at the backup. But also the thing that, as it says here, workloads use more resources than just CPU. So we tend to focus a lot of times on CPU, where latent demand can also be due to other sort of resources. In this presentation, I'm really focusing on CPU as the factor in latent demand. But understand that there's other things like scheduling of work. I mean, the case where you might have jobs backing up because of scheduling requirements or the way the scheduler works, and things like that. As we always say, when you think about driving down the highway, if you're waiting on the ramp, if you're trying to get onto the freeway, think of that as latent demand. You're not on the freeway driving, but you're sort of waiting to get on the freeway. Just to complete the discussion, I'm sorry, I have my thing here. Just to complete this discussion, we also have what we call the concept of induced latent demand. And what induced latent demand is kind of interesting, because that's work that hasn't come into the system, but would if the capacity exists. So we're not talking about work where maybe you've hit enter and the work is backing up. What we're talking about here is work that's not getting done, maybe because of users' expectations. The example there would be, as we say here, ad hoc queries, which, I might have a bunch of queries I want to run, but I tend not to run them because the system is slow and things are backed up. So I really kind of don't run those queries, or I don't run these compiled jobs or whatever it is. Eventually they have to get done, but what induced latent demand is the case where the work is kind of artificially being held back due to the fact that we maybe don't have enough capacity because we are in peak periods of time. And if we didn't have that situation, then what would happen then is more users would maybe hit enter, more users would submit jobs and whatnot. So just be careful of that, because the case we always see, or case often we see, is customers that have a lot of latent demand, they have resource capacity constraints or whatever, but then as they get more capacity, or maybe the caps are taken off or whatever, users say, oh, look, everything's looking great now, I'm going to do more work. And that more work, yes, it has to get done, but sometimes it's one of these things where it ends up being more because the things are faster. So just be careful of that. But when does latent demand actually build up? And typically what latent demand does is build up because of really two factors involved. And it's really a combination of these two factors and how they are actually interacting with each other. Obviously, one of those factors is resources, where given a particular workload's demands, they're going to need resources. So if you don't have a set of resources for a particular workload, then obviously that workload could back up as it wants to use the CPU. So resources, again, such as CPU in this particular case. The second cause, of course, could be due to workloads. Given a particular amount of capacity, it's very possible that the workloads themselves are placing too much demand on the resources. So it's not just a case where I don't have enough capacity. It could be I have plenty of capacity, but something changed. I mean, I'll talk about what some of the things that change are, but maybe a spring workload or a seasonal workload. It could be because one machine failed and now this one machine has to have all this new work on the system. Maybe we have a new workload on the environment, maybe a brand new workload, which doesn't happen very often these days for mainframe, but let's say a new workload coming into the mainframe environment, and now that new workload, for whatever reason, is placing extra demands on the resources. So it's really a combination of usage of the resources and the workloads. So this is what it's saying here. Why would available resources or workload demands change? Well, resources become constrained for a number of different reasons. You have the machine constraint. Maybe the workloads outgrew the machine. You have the LPAR level constraints. Maybe you have a 10-way machine, but this particular LPAR is only configured with 5 logical processors, and it outgrew those 5 logical processors. There could be capping constraints. We all know about capping, and there's all different types of capping. There's defined capacity limits, there's group capacity limits, absolute caps, group absolute caps. So capping could be a factor where normally maybe you do have enough capacity to run the workload, but for whatever reason, a cap is instituted, and as a result, you're artificially lowering the capacity that's available to the workloads. There's weight enforcement. Crossover is another example where now I'm maybe don't have enough zip capacity, so I'm crossing over to my CP engines, and that causes extra load onto the CP engines. So resources becoming constrained is a factor in creating latent demand. Workloads can also place additional constraint on the resources themselves. So as I said, it's not just we don't have enough resources. It could be that the workloads, changed for some reason. And this is the typical example where we have peak periods of time, where we have nighttime peaks and daytime peaks. We have seasonal peaks. We have market open peaks. It could be that the workload grows. It could be that you have new workloads. It could be because of failover. One machine fails, and for whatever reason, you're temporarily running the work on this machine or this particular capacity. There could be unexpected ad hoc activity. There's lots and lots of reasons why we have more workload. And rescheduling is another reason. Sometimes we reschedule workload to different periods of time. So I always like to show this chart. And what this chart is helping me understand that for you folks who are performance analysts, you know that you, in the mainframe environment at least, you have 3 primary performance responsibilities. I'm not going to go through them in any great detail in this particular presentation, but understand that your 3 responsibilities include, optimal workload performance, which means we have to get our workloads performing optimal. We have optimal resource usage or resource optimization, which means given the resources we have, we want to make sure we use those resources as effectively and efficiently as possible. And then finally, in the mainframe environment, we also have this crazy thing of optimizing MSU usage so that your software bills are in control, that you're not paying more software costs than necessary, or that you can afford because you're using additional capacities during peak rolling for our averages and all crazy things like that. The point is that what happens is when we want to, tune our workloads, when we want to optimize our resources, when we want to maybe cap or whatever it is to control our MSU usage, a lot of times there's going to be a give and take. Each one of these responsibilities that I list on this particular slide has a cost, and the cost is typically to one of the other responsibilities. For example, you can always optimize the usage of resources, and one of the ways we can do that is get rid of a workload or cap a particular workload or put a workload down at a low CPU dispatching priority so it doesn't get CPU when it needs it. Or a way we optimize workload performance is maybe we have to get more capacity, or maybe we have to use our capacity better. So there's give and take to each one of these. The issue is that as we do optimal workload performance, resource optimization, and optimal MSU usage, there's going to be give and take, and a lot of times that results in some amount of latent demand. Or another way you can say it is there's usually some sacrificial lamb that is going to suffer because we cannot get all of these in tune because maybe we don't have enough capacity, maybe we have too much workload given our resources, or maybe we just have to adhere to some resource restrictions for software pricing. So you want to make sure that when you do get that latent demand, that the latent demand is occurring to the workloads you want to have happen. And that's a big theme when analyzing latent demand. Not just the fact that we have it or how much we have it, but is the workloads that are suffering the ones you want to suffer if we don't have enough of these, if we can't achieve optimal performance in all 3 of these areas simultaneously. So the way we address latent demand is not much different than any other performance issue. So there is get more resources or tune those resources, do less work, tune the workloads, tune the resources, and take advantage of certain controls that will artificially limit certain things like maybe not allow certain workloads to run, maybe cap certain workloads, maybe restrict the usage of CPU or cut the CPU to certain LPARs and things like that. Regardless, one of the first exercises you always have to remember to do when looking at latent demand is understand your latent demand. And that's what we're going to talk about for the majority of this presentation now, is there a little bit or a lot latent demand. If you have a little bit of latent demand, that's typical for most environments. But if you have a lot of latent demand, not that it's not typical, but you want to understand it, and you want to make sure that if you do have a lot of latent demand, a lot of backup of work, that the right work is backing up, the right work is suffering, and that the most important work is the work that is getting the CPU. What are patterns of activity? We've been to shops, of course, that, and I'm sure you've seen shops where sometimes the CPU utilization is pegged at 100% across the entire 24 hours of the day, or the entire 24 hours of whatever it is of the month end. That's an unusual pattern, but typically you have the typical peak periods, the low periods of time, and we want to understand that when the work wants to run, is it able to run, or is it suffering from latent demand? And when I say peak activity, I'm not just talking about the typical camel hump where we have our daytime peaks and our batch peaks. It could be that for one particular workload, its peak is at a low period of time for CPU usage, which is a good thing. The point is, when the work wants to run, is it able to run? And if not, is it backing up? And that's what we call the latent demand. And as it says here, what workloads are suffering? Okay, so are the right workloads suffering? So let's take a look at some ways we can look at latent demand. And the first thing we usually like to do is find periods of time when the latent demand is actually occurring. And that's what we really want to do first. So the typical thing you do, and I'm sure many of you do this in your shops as well, is you'll look at, patterns of activity where in this particular case, I'm looking at the machine's utilization. And in terms of machines utilization, I'm looking at multiple days. You never want to do anything on one day. You want to look on multiple days. But in this particular case, I'm looking at 4 or 5 days worth of data from a month-end period of time. And you have to kind of notice your patterns of activity to see, is there a possibility of latent demand happening? In this particular chart, what we see is there are several times that the utilization of the processor, the machine itself, is peaking out at 100% utilization on average over a 15-minute period of times. One can assume now that we want to run, but the machine capacity is what's limiting us, and that's what's causing the latent demand, because we have workload that wants to use probably more than the capacity that this machine is actually delivering. But you also see here that we have other patterns of activity that I've circled, which is sort of this flatlining at something, in this case, of 80%. And you're like, why would I flatline at 80% when I have all this capacity? And many of you, of course, in the mainframe world know that because of software pricing, rolling 4-hour averages, contracts with software vendors or whatever, we have to limit the amount of CPU available to our LPARs or available to certain workloads that's going to cap them. So we're artificially lowering the constraint. The point is, relative to this chart, is notice patterns of activity. And in this particular case, we see the pattern of activity of regularly meeting 100% utilization and the pattern of activity of regularly capping, or whatever it is we're doing here. It's things like that that you want to recognize and see if it's happening, because that's typical signatures that latent demand is happening. So here it is blown up in the one day. This happens to be October 3rd, which is a peak period day. And of course, we see here again, we're peaked at 100% utilization. And here we see that we're flatlined, and it's that flatline that's concerning me, because of course, it's that flatline that is probably due to the fact that we have some sort of cap involved due to software pricing, which is frustrating at best that we have this machine capacity, but because our software vendors and the way IBM structured software contracts or whatever, they do this crazy thing of having to, cap the workload so we don't use more than a certain amount of CPU. So it's those periods of time that we know we want work to run, but we just can't seem to get it to run because of these artificial restrictions, as well as these physical restrictions. The other thing you want to look at, though, which is also interesting, is percentage of the weight consumed as a pattern of activity. Now, this is a measurement that we've been talking about, I've been talking about for 15, 20 years, if not longer. But the basic point here is that we know that we have our LPARs. We know that our LPARs have LPAR weights. And so the issue here now is that our LPAR weights are going to do a certain, allow the LPAR to be guaranteed a certain amount of capacity or certain amount of CPU. So in this particular case, what we're looking at here is the magic number on this chart is 100%. And what 100% means is that this LPAR used its guaranteed share. If I have an LPAR that is guaranteed 60% of the machine and it uses exactly 60% of the machine, then it used 100% of its weight. So what happens is we look at LPARs like this on the very left, which is using much more than its weight. And that's typically because, the other LPARs don't have demand, and because this LPAR has demand, it's actually able to use more than its guaranteed capacity. And we look at patterns like that. What's interesting about this particular pattern is we see that we have an LPAR during that peak, during that capping period of time, where the LPAR collectively, along with the other LPARs, want to use less than their guaranteed share. Nobody wants to use more than their guaranteed share. And that's interesting only because if these LPARs had the available capacity and not been artificially limited, then we wouldn't see this flat line below their guaranteed share. Basically, what I'm saying is they guaranteed a certain percentage of the CPU, but they're not even reaching that because something is happening. Of course, you probably know it's due to capping. So look for that sort of flatlining of things like LPAR weight enforcement as well, or percentage of LPAR consumed. Another thing to look for that identifies periods of time during capping is when you see changes in the pooling of the processor, or you see changes in the parking and unparking of the processor. Now, this particular example is not very interesting, but the basic concept here is that I have some medium and high pool processors, and then when this cap goes on, in this particular case, as I said, we probably know it's a cap, we change the pooling because now this particular LPAR is guaranteed, and not so much guaranteed because it's limited in the amount of CPU it's allowed to have. The result is that it's going to have a different sort of weight, hyper dispatch pooling, where now I have one less high pool and one more medium pool. But you can see here on the right-hand side from a parking and unparking point of view, all the processes are unparked. So that's not changing very much. All that's really changing here is the pooling, which is going to affect the dispatching of the high pool CPUs and things like that. So in other words, we're going to have CPUs that are not guaranteed to us. Again, signatures of periods of time of latent demand. Another thing we look at, not to spend too much time on it, again, if you're doing these billing contracts, one of the things we're always interested in is when are you reaching your maxes for the month? When are you reaching your peak MSU usage for the month? So here's like 11 days worth of data where the red lines indicate I hit my peak of the month. And in this case, if each one of these thin green lines and thin red lines means a 1 hour interval, you can see here I have many intervals simultaneously together where this particular LPAR is reaching its peak at MSU usage, and as a result, it's usually periods of times like that when you see lots of intervals, in this case, I don't know, let's say more than 30 intervals or whatever it is, if you put all those red lines together, that I have the LPAR wants to use more CPU because it's somehow being limited, or at least in this particular case, we know not only is it limited, but it is a constant peak. And usually when you see constant like that, day after day after day, it usually means this particular LPAR, its workloads want more CPU than it's available to it. In this particular case, again, due to a capacity constraint, due to licensing of software. And of course, the other thing you look at, and I'm sure you've all seen this, is cases where we have our defined capacity limit for this particular LPAR is here at 300 and some odd MSUs. We have our interval MSUs, which is how much MSUs we're using on a regular basis. But then we see here in the circle, we have a divergence of the actual rolling for our average and the billable rolling for our average. The actual, the rolling for our average is the easy one. We're just getting this rolling for our average. So of course that's above the defined capacity limit until it, kind of peters out. It's going to stay up there until we have the rolling for our average just kind of goes below the defined capacity limit. But in this particular example, we see a divergence of the green line here, which is the billable MSUs, because we know we're going to be billed on the defined capacity limit. So that's where we're being limited now, because this is the MSU usage. And so the point is, we know now here that we're being capped most likely, because in this case, we went over the rolling for our average, went over the defined capacity limit, and that's when the capping occurs. Again, signatures of periods of time when typically we get latent demand. So it's not just about reaching high capacity limits, it's also about capping. So one of the things we always like to do when we look at our customers is we always like to understand what kind of limits do they have imposed on the LPAR, because it's usually these limits that are causing the latent demand. So in this particular case, I'm looking in terms of MSUs, but in this particular case, we see here that we have the machine's capacity limit, which is how many MSUs are configured to the machine, and is that a limit? In this particular case, because the number of logical processors is equal to the number of physical processors, the LPARs constraint, the number of logical processor, is what's going to constrain the workloads as well. The green line here is our weights. Yeah, the weights may not be enforced, but when the weights are enforced, obviously that's going to be a constraint. And in this case, it's due to so many MSUs as well. So in other words, we can look at our weights and say, this weight represents this many MSUs if it's invoked. or we have defined capacity limits, which I'm showing here in the pink line. And you can see here in this particular case, that's the actual limit that's being imposed. Had this defined capacity limit not been here, one of these other constraints would have hit. Actually, we know that here, that the 100% utilization of the LPAR and of the machine also hit, so we can expect latent demand during these periods of time as well. So the point is just looking for periods of time that you have latent demand. The thing I want to mention, though, which is important to understand when looking at latent demand, is not all capping periods of time result in latent demand. You can have an LPAR that is severely capped, but not affecting the LPAR at all, not affecting the workloads at all. And that's because there's no demand for CPU during the capping period of time. So for example, if you look at the graph on the left-hand side on this particular slide, we see here that the orange line, this line that I'm showing here, is the percent of the interval that the LPAR was capped. And so we see here that we go along the entire day until we get to that flatlining I showed you earlier that we now know is probably capping. And we see here, oh, okay, we're going to cap. And so now we have this severe cap going on for several hours, about 4 hours. But what we're looking down here at this bottom line is the demand for CPU. So in this particular case, we may be capped, but because there's so little demand for CPU, I'm not expecting to see a lot of latent demand. I'm not expecting the workloads to be suffering. So just because we're capped doesn't mean we're suffering, doesn't mean we're going to be incurring latent demand. On the right-hand side here, I'm trying to show you the number of CPU delay samples as seen by Workload Manager. And in this particular case, I just limited it to 2,000 just to show the scaling when you see the next chart. But the point is, we actually have a small amount of CPU delay, and you can see that it just means that the workloads aren't really demanding a lot of CPU. Now you contrast that with this particular slide, which is the LPAR that I'm interested in, which is my SysA LPAR on the other slides. And we see here, we go along all day long, we're not being capped, and then boom, all of a sudden we're being capped for the same 4 hours. But notice here that the demand for CPU, this sort of blue line here, is very heavy. And this is an example where in this particular case, not only are we being capped, but the demand for CPU, because it's hitting 100% here, is probably beyond our cap. In other words, had it been the blue line been in the middle here, then we could say, all right, we're capped very severely, but at least we don't have full demand. Here we have the cap and we have full demand. Again, a signature that we have latent demand occurring. And I'll get back to CPU delay samples in a bit, but you can see here on the right-hand side, this is the corresponding CPU delay samples, where on the previous slide, we had a few hundred samples. On this slide, we have hundreds of thousands of samples. And you can see here that this activity here, this demand for CPU is resulting in samples. Again, a signature that we have some sort of latent demand period of time. So now what we want to do is, well, what is the latent demand? How much latent demand do we have? And what actually is suffering from the latent demand? And there's certain things we can do. Remember, we can't always quantify what the demand for CPU is, had that backed up work gotten the CPU, but we can actually see and kind of estimate it when the time comes, what the demand is, what we do. So you've all seen charts like this before. This is our chart where I'm trying to show, in this particular case, 3 primary numbers. We have the workload utilization. So for a particular LPAR, this is for a particular LPAR. So we're talking about logical constraints here. We're looking at the workload utilization, which is how much CPU time we can account for towards our workloads. Not very interesting. It's just the amount of CPU time that we can account for towards all of our WLM service classes and report classes, what our work wants to consume. We see here the green line, or this middle line, is the LPARs utilization, how much CPU we're using of our logical capacity. So in this particular case, we have so many logical engines. What is the utilization of those logical engines? And you know that if we take the delta between these two, that's the uncaptured. So we can eventually get the capture ratio, which is not the scope of this presentation. But then the other number we're interested in is this MVS utilization, which is a sort of controversial utilization, because it's not really a utilization, because what it really is the percentage of the measurement intervals that the LPAR went into what we call involuntary waits, or what we call time to wait. And I'll explain that in a minute, but the point of the exercise is we can think of it as the top line as being the demand for CPU had this LPAR, had the workloads, had more capacity given to it. Think of this as how much CPU they would actually consume, where the green line here, the middle line, is how much CPU they were allowed to consume. We actually see here before our capping period of time, when we know the machine was at 100% utilization, and we know that this particular LPAR's number of logical engines equals the number of physical engines, that when this LPAR reaches high utilizations here without the cap, we're actually hitting the machine capacity here that I'm pointing to, where here we're hitting a cap. The point is that we see that this top line is our demand. And that's because, and many of you have heard me talk about this before, is we look at MVS utilization as time to go into a wait state. I have a good presentation out there if you go to our website that talks about the history of the SMF type 70 record. And the very first measurement, and originally the only measurement in the SMF 70 record was time to wait. And what that means is that time that the workloads voluntarily gave up the CPU, that they went into a wait state. Because what happens is when you get dispatched by the processor, when you get dispatched by Prism, for example, you're dispatched for a fixed period of time called a dispatch interval. How much time that is not relevant. It's a few milliseconds, but you're dispatched, but it changes occasionally. And then once you're dispatched, one of two events can occur. The logical processor is dispatched to the physical processor, and the workloads in MVS are running. And then somewhere in the middle of that, we go into a voluntary wait, which is a way of the LPAR and its workloads of saying, look, we have gotten enough CPU. We don't need any more CPU. We're done. And so what Prism will do is take away the CPU from the logical processor, take away the physical from the logical processor, because it can give it over to some other LPAR. And the point is, because we didn't use the rest of our dispatch interval, because we went into a voluntary wait, then we think of the black line as being our sort of LPAR time. That's what LPAR utilization is based on. And we think of the red line as being the amount of time till we went into a wait state, and that's what MVS utilization is based on. And in this particular case, we see that they're both the same value, which we can think of as saying MVS and its workloads got all the CPU they wanted. If I go back one slide, we see that this is those periods of time we see on the left-hand side here, because LPAR utilization and MVS utilization are very similar to each other, because we kept on going into voluntary waits. We kept on having all the CPU we needed, and we just gave up the CPU voluntarily. It's when the time to wait exceeds the dispatch interval that you start seeing a divergence of the LPAR utilization and the MVS utilization. And this is the case where we get dispatched, so the logical processor gets dispatched to the physical processor. We're running. And by the time the end of the dispatch interval comes, the workloads and the MVS operating system still have not voluntarily given up the CPU. But Prism takes away the CPU anyway, because you used up the rest of you used up your dispatch interval. So this black line here is what our LPAR utilization is based on. But because the MVS and its workloads didn't go into a wait state, the clock is still ticking, so that time is going to be much larger. And this is a case when we calculate a utilization based on this longer line at the bottom here, and we calculate the LPAR utilization based on this black line here above it, we see that we're going to get two different utilizations. So again, to go back a slide, that's where we have a divergence of these two numbers, and this is time until wait. If we never go into a wait state, then we're always going to be 100% utilized, or we think of it as I always have demand for the CPU. I'm never voluntarily giving up the CPU. Again, when you see a separation, that's a signature that we probably have latent demand. We most certainly have latent demand. But I do want to point out a couple of things real quickly here. Is in this particular case, one of the things we're also interested in looking at is LPAR utilization based on configured CPUs versus LPAR utilization based on configured CPUs that are unparked. Now, in this particular case, it's not very interesting because the number of logical processors in this case is only 3. We saw that we have medium and high pool processors, which are always unparked. So as a result, if I calculate an LPAR utilization based on the number of configured logical processors, and I calculate a second utilization based on the number of configured logical processes that are unparked, they're going to be exactly the same number, and that's what we see here. But I do want to show you another example, which is another indicator, and I'll show you why I'm showing you this as it relates to latent demand, is this example. This is an example from a different machine, a different LPAR, where I wanted to show you that the number of logical processors is different than the number of, I'm sorry, not the number of logical processors. The number of unparked logical processors is different than the number of configured logical processors. In the previous example, the number of unparked and configured logical processors were the same. In this particular case, I have a partition that has some number of logical processors. They're in a high, medium, and low pool. The main thing is that there's a low pool set of CPUs, and sometimes those low pool processors are unparked, sometimes they're parked. Again, when they're all unparked, it doesn't matter to this discussion, but when some of them are parked and some of them are unparked, you can imagine then if I base the LPAR utilization not just on the number of unparked logical, configured logical processes, but configured logical processes that are unparked, we now see a divergence of LPAR utilization. So let me explain here. In this particular case, this is my MVS utilization at the top, right? I hit 100%, no different than the other machine or the another LPAR. The blue line here is our traditional, what we call our traditional logical utilization of the LPAR. So this is a logical utilization based on the number of configured logical processors. And that's what this is. This is what you'll see on your RMF and CMF reports. But then you say to yourself, when it comes to latent demand, when it comes to evaluating MSU usage, is it really fair to look at the number of logical processors that are configured? What about the ones that are parked? I can't run on that. Isn't that influencing my latent demand? And the answer is yes. If I have a parked logical processor and I have work that wants to use that CPU capacity and it can't because maybe it's parked because some other LPAR is using it, then I want to understand that when it comes to latent demand. And that's what this middle line is. What this middle line is my LPAR utilization of just unparked logical processors. Now, the reason I mention this is that if I'm looking at latent demand, the true latent demand that I'm probably interested in is the delta between these two lines, because that's something that is happening at this moment. If I want to look at latent demand based on the configuration, I would have to make it based on this bottom line here. And the only reason I mention this is because there's there's two different ways of looking at latent demand. Do I base it on configured logical processors or just configured unparked logical processors? It only matters if you have an LPAR where you have low pool processors and sometimes they're parked and sometimes they're not. You want to kind of keep that in your mind when you're evaluating your latent demand, which of these different utilizations you might want to use. The other thing you want to look at in terms of latent demand is the number of units of work that are trying to use the CPU. So we've now established that we have these capping periods of time. We have this divergence of MVS and LPAR utilization. But when we think of latent demand, we think of, all right, queue buildup. We think of work that wants to run that's not able to run. So we have to start evaluating at that level. And one of the ways we do that is we look at the min, max, and average amount of units of work waiting to use the processors. So what's happening here in this particular chart, what happens is the data gatherers like CMF and RMF are constantly looking at the queue of work waiting to use the CPU. And it's looking at the number of work units. What's a work unit? A work unit could be a PGM equals, a thread, a TCB and SRB, a program that wants to use the CPU. We're not talking about address spaces here. We're talking about things that want to use the CPU, like programs, threads, PGM equals, things like that. Typical work that we want to run to use the CPU. So what's happening is the data gatherer is going out every quarter second, or whatever it is in terms of your RMF cycle or CMF cycle, and it's sampling the length of this queue. So naturally, if it's constantly doing sampling during a 15-minute period of time, it can figure out what was the largest queue length found, what was the smallest queue length found, and what was the average queue length found. So what we're doing now is we're getting insights into the backup of work waiting to use the CPU. In this particular example, what we see during our capping periods of time is, let's take this point I'm pointing to here, is that we're reaching a case where, well, at times during the measurement interval, I have no queue buildup at all. So at times when no work wants to run, and that's because the min is a very small number or 0 in this case. The max is up here where we see we have hundreds of units of work wanting to use the CPU, but don't forget we only have 3 CPUs. So that's craziness that we have hundreds of units of work that want to use the CPU. But to be fair, a lot of monitors, a lot of work in your system has very bursty activity where it just throws a lot of work at the CPU. The work is very quick running, so it doesn't kind of build up on the queue. So many times we do see maxes being much higher than the number of CPUs. But what's interesting here is that the average queue length is 47. So here's a case where I have 3 CPUs, but I have an average queue length of 47. I now know that I have a backup of over 45 units of work waiting to use the CPU. Again, picture going to the bank and now there's a whole queue of 45 people that want to use that, get to the bank tellers. That's what this 47 is representing. That's craziness. Not that it's unusual. It's just the point is you only have 3 CPUs, but now I know I have a queue buildup of 47 on average. Sometimes the queue is much larger, sometimes the queue is smaller, but we see the average itself is much higher. We look at numbers like this, especially in the batch environment, when I see customers have 3 batch initiators, but they have 50 batch jobs that want to run on average. It's work like that that you kind of look at and say, well, that's latent demand. We need to address that. We need to tune this situation. So looking at the average number of units of work waiting to use the CPU is very interesting. Then the other thing we like to look at is, as I said, the data gatherers are going out there every quarter second and sampling the queue length. And what they actually can also do, and what they do is add sample counts to a series of buckets. And the buckets I have listed here on the right-hand side. And what these buckets represent are queue lengths, right? So the first bucket, this one up here I'm pointing to, is work units less than or equal to N, which says that there's no queue buildup, right? So it adds a tick mark to that bucket when it sees that there's no queue, that all the CPUs are busy, but no work is waiting, or some less number of CPUs are busy, but no work is waiting. But maybe you have the second bucket, which is all the CPUs are busy and there's 1 unit of work waiting on the queue. So it adds it to that bucket. And you can see here that these buckets eventually have, like this one I'm pointing to, is work units N plus 21 to 30, which means all the CPUs are busy and there's between 21 and 30 units of work on the queue waiting to use the CPU, all the way down to the bottom here, which we have buckets that represent all the CPUs are busy and more than 150 things want to use the CPU. And then what happens is you take all those samples and you can represent it as a percentage of the measurement interval or percentage of samples. So we think of each one of these columns as a measurement interval. And if we look at it as a percentage of samples, what we see here on the left-hand side is we have huge percentage of samples where we have no or small queue buildup. And then we see during our capping period of time, we have lots of buildup. The reason this is important to understand is that before we had an average of 47 units of work that wanted to use the CPU, but now we get an insight into, well, how often was it above that 47? How often was it below the 47? And what's the mixture? In this particular case, we see large queue builds up for periods of time, and we see small queue builds up for periods of time. So it gives us a feel for that. Now, this particular chart, the RMF and the CMF data, is based on the number of online, unparked CP and zip engines. It's unfortunate the data gatherers can't separate the CP work away from the zip work, but that's just the way it is. So we say to ourselves, what's unhealthy latent demand? And in this particular case, unhealthy latent demand, we consider anything more than twice the number of CPUs that are configured. Now, if you're not using the zips that much, we don't count them, even though you have zips. We really count the CPUs you're using. In this particular case, I will eliminate the buckets, if I go to the next slide, of the periods of time or the buckets that I don't care about. In this particular case, I have between 3 CP CPUs and 2 zip CPUs. So twice that is 10. So I say, all right, what I want to do is I don't care if I have queue lengths of less than 10. So what I'm doing here is I'm just getting rid of those buckets. And what I'm left with is something interesting, which is the periods of time that I had what I would consider unhealthy latent demand. And because of the color indications, because we have these buckets, we see how severe the latent demand is. If I got rid of all my healthy latent demand and I saw that I had very little of these deeper buckets here, I might not care about the latent demand that much, meaning, all right, I have latent demand, but it's really not that much. Where here we see a buildup of the red, which is saying that we do have large queue lengths building up as well. So there's periods of time like this that we take a look at, but now we get a feeling for how much latent demand we actually have. that times the queues do build up to 150, but most of the times they're sort of in the, what is that, 11 to 50 or 60 range, which is the purplish. In fact, if I overlay the two charts of my latent demand queue lengths and I look at it relative to my LPAR utilization and my MVS utilization, when I'm at 100% utilization, you can see I have latent demand. And when I'm at that capping periods of time, you can still, I still have the latent demand until it falls off, which is how the rolling for our average falls off. The point is you can see a correlation between the utilization and the amount of latent demand we have. You can even see here that latent demand builds up during this period of time. Another indicator of latent demand is if you look at your performance indexes. Typically during latent demand periods of time, during capping or weight enforcement or whatever it is that's causing your latent demand, if you have more work that wants to run than is able to run, and your goals, your WLM goals are well tuned, then what you typically then see is you see the work suffering due to the fact that we are not giving the workloads as much CPU as they want. Now, in this particular case, we can see here on the right-hand side that during periods of capping, we see that we're suffering, not just capping, but we're hitting 100% utilization. We're suffering, our performance indexes are suffering here. So we do that we see that as an indicator of latent demand, which what is unfortunate in this case, which is interesting to observe, is that even the high importance workloads are suffering. Now, that's kind of frustrating because we see here that the high importance workloads are suffering. Why are they suffering, and is it right for them to suffer? Or maybe it's just that we, have too aggressive of a goal. I don't know. The main thing is we want our lower importance workloads to suffer, but at the high importance workloads, we want to understand if they're suffering, are they part of this latent demand mix? It could be that the reason the high importance workloads are suffering is because they don't have a good CPU dispatching priority. Maybe they're down at the bottom of the dispatching priority order, and as a result, that's why they're not getting CPU. They're down at the bottom, WLM is not helping them, or maybe it's too late to help them right now, and as a result, their goals suffer. So we need to investigate all of that as well. Another indicator of latent demand, of course, is our utilization. We saw that we have our LPAR utilization, but how is that broken down by workload? So here's a case where we look at CPU usage by workload, and one of the things we notice here is that we have these low importance workloads, these low important workloads that have high demand for the CPU here that I'm pointing to. The reason that's interesting to observe is if we look at the utilization of our regular workloads, these are our, let's just say these regular workloads, meaning these higher importance workloads, we see that their utilization continues onward. We don't really see a huge change, maybe a little bit of a change. What we do see is during the capping period of time that we do kind of see a flatlining of these workloads. So hopefully what we're going to see when we look at other data, that when we do have our latent demand that we identified it as our low importance workloads, and that they're the ones that are suffering. So that's what this is showing, is a CPU by workload. And now we know that these workloads, these low important workloads, are the biggest consumers of CPU. So then what happens is you correlate that to your delay samples. You think to yourself, I have this work that wants to use the CPU, but I know I'm being capped, so is it suffering from delay of CPU? And now we can use the delay samples as indicators of not just which workload is suffering, but how badly they're suffering. We can't derive the amount of CPU they would have consumed, but we can actually derive the severity of the latent demand in terms of demand for the CPU. Is this work that constantly wants to use the CPU, or is this work that wants to use the CPU, but when it gets the CPU, it doesn't use a whole heck of a lot of it. It just happens to be backing up. And that's what we're using the delay samples for. So in this particular case, we see here that our low workloads, our important level 5 workloads, are the ones suffering from tens of thousands of delay samples. And that's what we want to see if you're going to be evaluating latent demand from a control point of view. We want the lower importance workloads typically to suffer. But you look at something like sysstc here, even that's going to have delay samples. But you say to yourself, well, that's not good. Well, the answer is right, it's not good, but just know that all work in the system is going to get delayed. But hopefully what we're going to see with something like sysstc is that although it has some amount of CPU delay, I wouldn't necessarily count it as something that is suffering from latent demand, because all work gets delayed, and when this work is delayed, it's not a whole heck of a lot of delay. So in looking at latent demand, we not only want to look at the concept of work is backing up, but when we say that all work backs up to a certain amount, the work at the front of the queue, that when we do have available capacity, if it's able to run and runs very quickly and is not and it's not backing up, then one can assume that the latent demand is occurring in them, but the lower importance workloads are suffering the more. Don't think of the high important workloads as always being the ones that are suffering the latent demand, I guess is the point. If something is using the CPU, make sure it's the high importance workloads. But it's also interesting to look at CPU using samples. You say to yourself, well, if I have my utilization and I have my delay samples, now I know what's backing up and I kind of get a feeling for how much CPU is being delayed. Well, you also want to look at using samples, because you say to yourself that in this particular case, I see my biggest consumers of CPU are also these low importance workloads. Yeah, the high importance workloads are using the CPU, but the fact that the low importance workloads are using a lot of CPU says to me that yes, we have latent demand, but at least the work that's suffering from the latent demand is also able to use the CPU for a bit. And that's what we're looking at here. Yes, we looked at the APPO percent to look at how much CPU they're actually consuming. This is just how much using they're doing relative to the delay. In the previous chart, we saw tens of thousands of samples that were delayed for these workloads, but here we see thousands of samples of using. So we know that they're using some, but they're delayed mostly. That's the way of putting it. So then the next level we look at is we say to ourselves, okay, we know we have work delayed for CPU. We know the work that's backing up due to the latent demand. Is it the right work, and is it appropriate that it has the latent demand? It could be that the work is suffering from CPU delay, and it could be because there's not enough CPU capacity available to it. But we also want to make sure that if we have this work that is suffering from delay, the latent demand work, we want to be able to control what that is. And one of the ways we control what it is by hoping or controlling that its CPU dispatching priority is below all the other work in the system, that you want to get the CPU before the work that you want to have suffer gets the CPU. So the next thing we do is we look at things like CPU dispatching priorities. In this particular case, we have lots and lots of service class periods. And what you typically do is you kind of look at the ordering of these service class periods. And I did this analysis, and what I could tell you is that the importance level 1 guys are at the top and 2 and 3 are in the middle. And what you're looking for is situations where high importance workloads are not down at low CPU dispatching priorities. We just landed up working with a customer recently that had their most important workload all the way down to low dispatching priority. And they never noticed it before until they had a problem where that problem gobbled up all the CPU. And now I have this important workload running down to low CPU dispatching priority for WM to recognize that it's not getting CPU and then hopefully build up its CPU dispatching priority upwards. That's the kind of situation you want to avoid. So what we're looking at here is CPU dispatching priorities, hoping that if I tune my goals, then the work running at the low dispatching priorities, which is also the same work incurring the most CPU delay samples, which is also the work that is at the end of my dispatching queue, is the work that's suffering from CPU delay, that is the work that's suffering from latent demand. So the point is, we've identified that we have latent demand, how much latent demand we have, and now we've identified the workloads that have that latent demand and what dispatching they're running at. And yes, it's very good that they're running at the low dispatching priorities because they're the lowest important workloads in the system. So evaluate your dispatching priorities. And what you also want to do is evaluate the CPU consumed by the workloads. Here's an example where I have a high importance workload, in this case DB2. We see that it has very little demand for CPU, relatively speaking. And when it runs, which is the blue case here, the blue is the CPU consumed, the gray below the blue is how much CPU it's leaving and making available to the lower importance workloads. So in this case, we see that DB2 has a high dispatching priority. It gets all the CPU at once, and it's leaving lots of CPU for lower importance work or other work. Where now I'm looking at that batch low, which is also running at the lowest dispatching priority in the system. We see here that we have all the other work in the system using up the CPU. Eventually it gets down to batch low. And by the way, when batch low uses the CPU, it uses up as much as it can use. And you can see it's not even leaving anything below it for other workloads to consume. And it's kind of like that you want to look at in evaluating dispatching priorities and evaluating latent demand. And then eventually you want to look at other things. You want to look at your WM goals. Here's a case where I'm looking at velocity goals. Now, this is not necessarily an indicator of latent demand, but it is an indicator that we actually had something happening, that work started suffering. And so we want to make sure that if the goals are not being met, we want to make sure that this is not the work backing up. We know from the delay samples that something called DB2 control is not backing up. It's just not performing that well because it is incurring more CPU delay than it's normally incurring. We're here, if I look at the DDF bat low, which is the lowest important workload, you see it's suffering greatly from a velocity point of view. In addition, other things you want to look at in evaluating latent demand is things like CPU per transaction. In theory, what's going to happen is if you're running at low dispatching priorities, if the work is backing up, we're going to end up using more CPU per transaction because the workload is never getting enough CPU, so it's constantly being redispatched. It's inefficient use of the processor caches. There's a lot of other stuff going on here. So during periods of time when we do have latent demand, we do have a buildup of CPU per transaction. That's important because now we know that we may be capping the workload to control our resource usage, but we're also causing the transactions to use more CPU per transaction. And then finally, we want to make sure that we do the same thing for our zip engines. In this particular case, you look at the zip and how busy are the zips and what's the average units of work waiting to use the zip and what's the distribution of that work and things like everything you can imagine we just looked at for the CP engines. You want to do the same thing for the zip engines. So it's no different of an exercise. We want to find out who's using the zips. But what you also want to find out in doing a latent demand exercise is you want to examine your zip crossover. Because what's happening here is that this happens to be an environment with a very healthy zip utilization, and there is work crossing over, and we do have honor priority turned on, which means now we have higher importance work running at high CPU dispatching priority that could have run in the zip engine, but now because we have honor priority turned on, is going to run in the CP engines at the dispatching priority of that high importance work, which is then pushing the lower importance work downward further and limiting its CPU. So the point is, in terms of looking at latent demand, you also want to understand if I have latent demand, is it being affected by the fact that I have work that could have run in the zip engine, didn't run in the zip engine because of crossover, and the reason I have as much latent demand as I have is because of crossover activity. So I actually thought I had one more chart that I wanted to explain something in terms of projecting latent demand, but I don't have that, but I see we're out of time. So I wanted to thank you for joining me this morning. Do we have any questions? Let me look at the chat here to see if we have any questions. Let me just do something real quickly here. As a reminder, I want to just point out that we do have the Mainframe Performance channel. So if you're interested, I'd love to have you as a subscriber of the Mainframe Performance channel so that perhaps I can give you some additional education. So let me just do something real quickly here. So any questions? Anna, any questions?
Peter, that was fantastic as usually. Thank you so much. I'm going to be definitely your top tier subscriber for the Mainframe Performance channel. I'm looking at the chat, there are no questions. So, I think that if anybody has a question, they can follow up with you later. So I can only thank you again for this fantastic presentation. Thank you so much. And thank you to all attendees who were with us today.
Yeah,
thank you.
Again, I really do appreciate you joining us today. Thank you very much for joining me. Enjoy how is the conference going? Is it going well?
Yeah, it's going really well, though, it's a different format now. It's virtual, so obviously everybody misses, the face-to-face interaction.
Right.
But it is what it is.
Okay. Well, for those of you, again, if you would subscribe to the Mainframe Performance channel, the other thing I wanted to point out is, again, we're giving a series of educational webinars. They're free. They're only a half an hour. We think of them as just, just keeping in touch with you, letting you know what's going on. And we have some really pretty interesting discussions we're going to be talking about. And so one thing we're working on now is like BCM RLS, if you're interested in data sharing. So please think about going and attending our webinars. Just go to our website, sign up, and I'm looking forward to seeing you there. So with that said, thank you very much. I really appreciate the invite to UK GSE. I miss being there. I really miss, well, let me ask you this virtually. Does everybody have their virtual background as, what was it called? What was the place called? What was the place where they usually have it called? I forgot what it's called. Well, Whittleberry. So, you know, maybe we will see you in Whittleberry next year. I think they moved from Whittleberry, but thank you, everybody. Enjoy the day. Thank you, Anna.
Thank you, Peter. We really looking forward to seeing you next year in another location or Whittleberry Hall, whatever it is. So
right.
thank you
Stay
so much.
healthy, stay healthy, stay healthy, and keep in touch. And we do miss you. I miss you. So hopefully we'll get to see each other soon. Thank you, Anna. Bye-bye.
Yeah, thank you, Peter. Bye. Thank you.